Well, we want to discuss the final topic of the linear system identification. It's lecture 17, Subspace Method for System Identification. And this is the part one, the realization. So as you can see here, we've been dealing with the state space representation, in common filter in particular. But we haven't done the identification part of this systems represented in a state space. So this subspace method is the method that you should use for getting the state space representation. So it's nice. You have a time series input and an output data. You just use this algorithm to get the software returns you with this matrices A, B, and C, D that covers both state equations and output measurement equation A, B, C, D. Okay, and then this turns out to be very useful. Yeah, very useful. But you see a lot of matrix operations. So if you are a little shy on the linear algebra and then, matrix operations, you need to brush up a little bit to understand these materials. But I'll just go through it step by step so everyone can understand. So far we focus on PEM, predictor error method, right? So, this is a very simple method in a sense, if as far as you just care the forward pass transfer function, G, and suppose the error, the noise is just a simple noise, a white noise coming into the systems, not the colored one. It is basically a type of ARX program. And you can just get the good solutions by using just a standard D square and estimate, right? And we know how the estimation process converges based on the central limit theorem that we can find the asymptotic behavior of the parameter estimation that as we discussed. In case you have a little bit of colored noise comes into this, you tend to have a biased estimate. So to get rid of it, there are a few techniques. And one is actually you get the predictor, including this H, and go for modeling like ARMAX, ARMAX model, or more complex one. But it turns out that the parameters involved in the for the transfer function G and then the noise dynamics, H, are non-linearly involved in the regressor. So you have to deal with the non-convex optimization problem. And it turns out that you can't use the standard least square estimate. Instead, we extend it and needing some repetitive computations, right? But hard part is really non-convex optimization. You may get stuck at the local minimum, right? So this is, there is some actually clever techniques, called instrumental variables method for unbiased estimation, but that's a little bit actually technical, and then lots of limitations applied too. So PEM, despite the simple structure, simple concept, having some troubles. Also, the obtained transfer functions need to be converted to a state space if you want to actually use the state space models, right? So there's an alternative method. It's called the subsystem method. Here we deal with the state equations and then measurement equation, output equations in the discrete time form. And then we want to determine parameters A, B, C, D directly. Interestingly, in here, parameter matrices A, B, C, D are linearly involved in these two equations, right? In fact, you can combine these two equations and rewrite it in this form. I put the xt plus 1 and yt together here, and then right-hand side, xt and ut are placed in this way. And then these two are related by matrix consisting of blocks A, B, C, D. So if you treat this as one big parameter matrix, not the vector, but a matrix at this time, and then the combination of ut, xt and ut as regressor phi t, this is a linear regressor. Yt is given by the product between parameter matrix and the regressor, right? So we can use just a standard least square estimate to obtain this. So that makes things much simpler. It's not actually non-convex optimization, but that's much simpler. Okay. So this simple idea first came out from Gopinath's work back 1969. So what he did is basically very similar to the algorithms called enforced these days. These two equations, and then now let me just introduce the dimensions, the parameters, and which you need to memorize and for today's lecture, the rest of the part. So state dimension is n, okay, and then input dimension is m, and then output is p. Okay, not the R, but P. We use the P for output dimension. And then the eta and the V are basically, are residues, not actually accounted by this model. This may be something, a mixture of many things, but let me put this one in this form. Okay. So as I said, rearranging these two equations, we can write this one this way. So I know this one is a type of linear regressions. Although this ABCD is basically a matrix, not the vector like this theta. But I know we can actually treat this one in the same way. Basically, I know you can just determine each column, or row of vectors involved in this, the theta, and then you can just put them together. So the solution to least square estimation is given by this, just one shot. Okay. So yeah, this phi, which is actually this regressor part that comes in here, and then back to back, we put this one in this way, and then take inverse. Sorry, a little bit actually, these two are actually locations are swapped in some way because of this change. But this is right, the equations, and then this part is output side, xt plus 1 yt, and regressor place back to back. And then that is multiplied to this inverse to the phi transpose. Good. So if we can do this, it's great. And also interesting is that, my first of all, the very good important point is that if you collect the data, which is basically persistently exciting, you are guaranteed to get the optimal one, convex optimization. So the conditions to support that is that when you write actually regressors, first one, the second one, up to say data point to n-1, but in this, this matrix, it's basically n-dimensional vector x and then m-dimensional input vector u all put together. If this one is a full rank, capital N is sufficiently large, so you have many data. Okay, so but each column vector together it's n plus m dimensional vectors, And if you put this one, that's actually spanning the whole n plus m dimensional space, meaning that these are basically full rank. Then you are guaranteed to get the optimal unique solution based on just a standard least squares. Now, another interesting point is that this residues, we left this one aside, but if you collect these and do this kind of computation, eta new, eta transpose, new transpose, put in this one, you get the something good statistics that can be used for actually Kalman filters, process noise covariance, and measurement noise covariance, and actually cross coupling between the two, S matrix too. Of course, there are lots of actually complex issues involved in treating this as a stochastic systems, because these are not necessarily stochastic stuff, and maybe something coming out of the just unmodeled dynamics, some nonlinear effects, or through some uncertainties and so forth. So we need a little bit more careful treatment in that. But basically, you can get some information as to the unmodeled part of statistics. Okay, so this is a wonderful method. As far as you put together the data, you can get the ABCD in one shot. That's great. Now, however, the key point is that see this, I just dealt with state X, XT, and XT plus 1. And then I said only, what we get is input-output data. So it's a little bit different, right? Input-output does not include the internal state. However, these expressions, basically using that, state vectors. Basically, state vectors are something unknown, and you have to construct that. So the key question here is how we can actually obtain the state xt, xt plus 1 from input-output data. Okay, and this question is directly related to our, system realization problem. So you get the a little bit, new terminology, system realization. So let's look at that. So system realization is actually the program given a input-output transfer function for linear time invariant systems. We'd like to construct its state space representation, which consists of state equations and output equations in this way. Now, what you know is that the given state space equations like this, and then convert them to transfer function. That is a very straightforward method. You just take the Laplace transform directly in here, and then eliminate the Laplace transform of x. Then you get the actually input-output transfer functions or transfer matrix. Okay, so that's from here to straightforward. But going other way is much more complex problem, and then it is the problem is called realization. The particular state space representation we want to realize, because of this actually, inverse map is not one-to-one correspondence. It's basically, the many ways of constructing the internal states. And among the many of them, what we like to do is first, actually, we want to use the minimum number of state variables. And then that is to give the lowest dimension of state variables. And then the ABCD realized in that way. It's called the minimum realization, minimum order realization. And then the good news is that the minimum realization is unique, okay? Up to a non-singular transformation. So state variables can be converted to other state variables, set of state variables through some one-to-one non-singular transformations, right? So you can't actually determine, to that point. Only you arrive at the unique ones, which is basically up to the non-singular transformation. Okay, so we need a little bit more kind of a system dynamics and controls background. So I just make the quick review, or for someone, this one is a lot of the new materials. So I'll give you some kind of a quick summary of the background information. So if you have some kind of difficulty, you just interrupt my talk today. If you are not clear, other people are not clear too. Okay, so first one is actually impulse response. Okay, and then the relationship to state equations. So suppose you are given there's actually state transitions and output equations. So let's start with this. Yt cxt plus dut. Xt can be replaced by using this state transition equation into axt minus 1 and a but minus 1, just a one-time step back, and then adding this guy. So you can write in this way. So xt minus 1 can be further extended to the expression using this, and then to xt minus 2, and then ut minus 2. And then if you repeat this process, you arrive at the x naught, which is the initial condition. And then every time you move backward, you have to multiply a repeatedly, end up with the a raised to the tth power, and then the dut, and collecting all these ut terms can be written this way. So cat minus and I minus 1, but minus I, and I equal 1 to t. Okay, so this is the expression of yt by using the state equation repeatedly. Okay, you arrive at the initial condition x naught. Now let's look at the impulse response. What is impulse? Impulse response, all initial state is 0, set to 0, and then you make the one shot, boom, the input, right? And then actually the rest of the part is the input kept to 0, right? So if you put that input on yt can be seen in this way. So t equals 0. That's actually yt is to pick only the first term. That's actually d ut, and then now t equals 0. So du naught, right? Du naught in the first equation. One. How about the t other than 0, larger than 0? Then actually say that let's see y1. Okay, and the first term here is actually because of the impulse response, the initial conditions is set to 0, so this goes out, right? So y1. y1, and that picks up only this term, So C. So you remember that the ut is non-zero. Ut is 0 and everywhere other than the t equals 0, right? So u1 is already 0, right? So here u0, that is actually since if we set the t equal 1, I equal 1 only is to survive. So I equal 1, so the CB survives here. And then in case of time t equal t, if I becomes a t, then actually non-zero, others all died. So you pick this term, I equal t. So this is the response you receive. That's impulse response. Okay. So actually, if you write the output to yt by using impulse response, this should be written this way. This is basically, convolution expressions, right? So comparing this convolution to GK and then this results, you can find that this convolution impulse response quotient matrix G of K can be written, this way. So, YT equals GT U0, and then U0, the G picks up only this part. So let's eliminate, U0 from here. That is, here, right? So T equals 0, just the D, and then T 1, 2, 3, it just picks this part. C A T minus 1B. Okay. So all I get is just using the state equations and output equations, write out this, and then relate this to impulse response, GT. Okay. Now, yeah, before moving forward, I have to introduce or review a couple of other concepts. One is observability is a very important concept. We discuss it in Common Filter too. And just to recap, reconstruct the initial state x0 from output to sequence y0, and y0, y1, yk minus 1. Okay, this is what you observe. Can you really reconstruct the initial state x0? Yes, you can if the system is observable, right? So, you can write out the output equations, let's assume the input kept to 0 to make an expression simpler. Y not equals Cx0, Cx1, write in this. So, x naught is involved in all of this. So, y's, if we put them together into a vector like this, x naught is multiplied to each of these, to write all these collectively, we get to this expression. So this is linear equations, y's versus, x0. In between, we have this matrix, which is called the observability matrix. If this guy is full rank, then we can actually determine x naught uniquely from y0 to yk minus 1. Now, just a simple case is that, suppose output is scalar. So dimension of output y, p is 1. And, we just pick the, n, n and output observations. And n is actually the dimension of the, state. Then actually this matrix becomes a n by n matrix. A square matrix, so if there's a case, this full rank means that this one's invertible. So taking the inverse to it, you can explicitly write x naught equal observability matrix inverse times this observation. So you can uniquely determine the original state x naught, right? Now, in the context of system identification, usually we do not know the true order of the system n. So k here is to be actually, we don't know the n. So we just take many, k, the large k, which is presumably, and then definitely I would say, larger than n, okay, larger than n. So this observability matrix is not really exactly the observability matrix that where this in a k equal to n, but then we extend it. So it's called the extended observability matrix. That's not actually a major issue to expand it, but it is important in the context of system identification because we don't know n exactly. Okay, the other thing is basically reachability or controllability, I would say. So suppose we look at the nth state that can be extended in this way, right? So initial conditions and input the sequence you use are actually piling up on here, and this as a whole can be written collectively in this way: matrix B, AB, AN minus 1B. And then the input the use can be written this way. This times this is to give this term, these terms, right? And then here, this matrix, replaced by C. Matrix C is called the reachability matrix. Reachability matrix, which means that consider if the initial state X naught can be transferred to any state at the time step n by means of sequence of input U0, U1, UN minus 1. Then you can bring the state to any state. Yeah, if this one is actually full rank, right? So that there, in other words, there exists an input sequence to bring this state to arbitrary state in the n-dimensional space. Okay. Now, what you learned is a little bit different. It's actually this guy is starting from origin to go any state in the dimensional state space. That's a reachability. What you know is controllability is very similar to that, but a matrix is non-singular, then this reachability conditions and then controllability condition are the same. And otherwise, a little bit different, but for today's discussion, that is not an actually important part. So you can think about it in the controllability matrix, in here. So, in the system identification, again, the n is not exactly known, so we expand it, k. This dimension is a little bit bigger than the, real state, and we use this and extended the reachability matrix. Now, here's an interesting point. Hall-Kalman's method for system realization. This particular theorem basically developed by Yuichi Ho. Yuichi Ho, sometimes called Larry Ho, is actually a professor emeritus at Harvard University. He is actually MIT's graduate. He is supposed to come to our department, the Department of Mechanical Engineering. For some reasons, by mistake, his application went to electric engineering. So he got the undergraduate degree from electric engineering of MIT. Anyway, he finished the doctoral thesis, which turns out to be very important work. And then one of them, actually, he collaborated with Kalman, and this particular theorem is a cornerstone of this system realizations, and had a very significant impact upon the subspace the method for system identification. So Kalman's method is foundation of subspace method, where state and measurement equations are obtained from impulse response quotient matrices. Okay, so consider our linear time invariant system that is both observable and reachable. Okay, and then as I said, if the system is observable and reachable, basically you can find the ABC matrix is to be kind of a minimum lowest order. If you put the additional state variables which are not independent, you can't achieve the observable and controllable systems representation. So controllable and reachable, that means that implies that the lowest dimension and then this ABC is basically minimum realization. So we first construct a block Henkel matrix. Now you just hear an unfamiliar terminology, Henkel. But this Henkel matrix is so convenient and a clever idea. And then actually, it's not that complicated at all. Okay, Henkel matrix. What is the Henkel matrix? Now, we place these impulse response quotient matrices, G1, G2, G3, in a very special, structure as shown here. G1 to place here, 1, 1 position, and the G2 is 2, 1, and 1, 2, okay, going up. And the G3 here, here, here. In other words, you have a sequence of impulse response matrices, and then we place it first G1, G2, G3, up to GK, and then actually cycle through it from G2, G3, GK plus 1. And then the next one, the G3, G4, GK plus 2. And then you repeat this K times, okay? And you can place this. As a result, as I said, G2 is placed in this way, kind of, the skew diagonal and the directions, they're basically going up the same, quotient elements going up this. This particular form is called Henkel Matrix. Okay, so we place impulse response quotient matrices in Henkel matrix form. Well, in fact, these are matrices, so it's going to block in a Henkel matrix form. Now, let's actually substitute. Recall that we have identified the impulse response quotient to be GT, T equals 0D, and the T equals 1, CB, and T equals 2, CAB, CA squared B, CA cube B. This is what we found in the previous slides, right? You remember that. So let's actually plug in these into this form. So we skip the G0, so starting with the G1, right? G1, CB, and the G2, CAB, and then this one CAB, the next one CA squared B, and going down this way, CA minus 1B. Okay, you place in in this way. The dimension of this matrix is a little bit complicated because its output side is basically C is p-dimensional, right? And then we have K of them, so K times P is the number of this actually row vectors, and the column is basically it's dominated by B's dimension. That's actually M. And we have totally M and K of them, so K times M. Okay, so that is the dimension of this big block Henkel matrix. Now, interestingly, this Henkel matrix can be decomposed to the extended observability matrix and the extended reachability matrix. So let's think about this. Think about this. This is the observability matrix, and this is extended controllability or reachability matrix. And if you just multiply this, the first one, C times B, that's here. And the next one, CA times B, that's sitting here, right? And also C times AB, this guy is sitting here, the same, right? So, if you just multiply these two, you get the original block Henkel matrix containing all the impulse response quotient matrices. So this Henkel matrix can be written as the product of observability matrix OK and the controllability or reachability matrix CK. OK, CK. Okay, so please remember that Henkel matrix OK, CK. Good. So here's the things. So what we do is to take the singular value decomposition of that Henkel matrix. When did you actually use the singular value decomposition last time in 2160? Maybe push back to partial least squares regressions, right? So perhaps you review that. So this is actually a rectangular matrix, can be decomposed into three products like this, right? And U is basically left singular vectors are all involved in here, and then this is the right singular vectors in B's, and sitting in between is singular values are placed in the diagonal form like this, right? So you remember that the all these singular values actually basically it's all positive, but because you remember that the singular values are basically coming from the eigenvalues of the matrix H transpose product H transpose H, basically they have the same eigen values. So if you put together back and forth, back to back H transpose or H transpose H, the matrix is at least positive semi-definite. So the eigenvalues are not actually negative, right? So you can take the square root of that. So this one is actually a positive number. We take one more square root, for this. So square root of lambda 1, singular values, square root. Okay, we can take it because this is positive. Okay, all positive in here. Then we construct this sigma, half a sigma. This is a little ugly notation, but interesting. Sigma is this part, right? Diagonal term. And then actually, square of that. Basically, if you make this, and then if you multiply two of them, you get actually recover the original sigma 1 diagonal matrix with the lambda, i's in the diagonal terms. So we can split this one into, sigma half. Okay, so in order to realize, actually go back to this, Henkel matrix is a product of OKCK, right? Now, we like to know OK and CK individually, but with this actually expression, singular value decomposition, we can actually make this kind of a term. OK consists of U1, which is actually coming from here, U1. These are zero, so don't worry, U2 and then V2, it's not relevant, but we focus on the U1. U1 times half sigma matrix, and then the CK side, half sigma, and then the V1 transpose coming from this part, okay, this part. So if you multiply these two, you can recover, putting this one this way, you get the H matrix, right? Simply, so defining this in this way, OK, CK, O, and actually CK, these two can be put together. So that's actually, H matrix. Cool. So we can determine the OK, CK individually, but, even though you put the non-singular matrix, square matrix T, to transform this expression to something else, and actually, T inverse in here. If you multiply these two, T inverse cancel out. So you can recover H. You can recover OKCK in the same way. So what this means is that we're not actually determining OKCK uniquely, but in fact, to the extent that actually non-singular transformation as involved here. But it's almost actually a unique representation. Okay. So from the above observability and the reachability matrices, we can determine the system matrices ABC in the following way. So now we know OK is this guy, right? So this is actually computable from the Henkel matrix. We can actually determine U1 and the sigma 1. So this is known now, right? So if you look at the OK, the first block is C, and the second block is CA, blah, blah, blah. So good thing, if you look at the first block, that C is there, which we want to determine. Okay, so I know this C, please don't get confused. This one is not the contributive matrix, this one is involved in the output matrix, output equation or measurement equation, Y equal C times X, plus D something, right? So C is basically, obtained, extracted from this, OK, U1, sigma 1, half. So you can just take this block, and I just use the MATLAB type notation. You take the first 1 to P row vectors from this matrix, right? And column side is actually all of them. So just this mark. So I hope this one's clear. And what I'm trying to do is to pick up only this guy, right? Likewise, the reachability matrix, the CK, a good thing you see the B just here, the front block. So you just extract the B, from this reachability matrix that can be actually obtained from the singular value decomposition of the Henkel matrix. So we just pick the first M column vectors from here, and that's written in this way. Now, so the remaining question is matrix A. We need to determine A. That's a little bit, needing a little bit more computation. But in here, to determine the matrix A, we examine the extended observability matrix. So this guy is original observability matrix, right? And let's multiply A from the right, okay? Post multiply A, then you get and shift this one block CA squared. The last one is CAK. So this is something one block, ahead. Let me write it as O sub K plus 1, meaning that it's starting from CA to CA. AK. Okay, so I know this particular matrix because we cut out this part of C, so I just used a little different notation, O prime K plus 1. Prime means that we don't have a C over here. Okay, so O prime K plus 1. The dimension is this. So now, again, this can be constructed, in the same way. So, this equation, the linear equation, A is placed here, OKA equal O prime, K plus 1. So solving this for A, we get the A, right? So, let's pre-multiply OK transpose. And remember that the OK is the dimension of PK and KP times the N, right? K is larger than N, okay? Now, pre-multiplying this, you get this, and so the dimension is N by KP, and then KP by N. If you multiply these, you get the N by N. And then if the system is observable, this particular matrix becomes non-singular. So you can take the inverse to it, and A equal this inverse, times this. And this particular part is basically a pseudo inverse of OK, right? So just a pseudo inverse times O prime K plus 1 is to give you the A matrix A. So therefore, the minimum system parameters A, B, C, D are directly obtained from the singular value decomposition of the Henkel matrix H, consisting of impulse response coefficient GK. So this is a story, and then the similar techniques we're going to use. Now here's the things, and we need to just figure out a little bit. So we started with the whole Kalman method, starting with the impulse response, right? So if we just use the some method to get the impulse response, then it's fine. I know that can be expanded to ABCD and the matrix that we have just seen. However, our original mission is that given some input-output data, then we like to find the ABCD. That's actually system identification, right? You learn the few system identification method, MOSIP or enforce-it. These methods are all actually convert time sequence input and output observations converted to ABCD matrices. So that is something missing. So we need to actually do something to replace or rewrite this actual impulse response in the form of input-output data. Okay, so now in Subspace Method, here's another Henkel matrix. We place input-output data into block Henkel matrices. So input data, again, U0, U1, blah, 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 UK minus 1, and one time shift, U1, U2, UK, and repeat this for many data you observe, UN minus 1 to N minus 2. Okay, so, this is a little confusing notation, but we use a capital U to represent this Henkel matrix, corrective representations of this input sequence on, having a two subscript. First one is to show the time index in here, and the second one is the final time index here. So U, capital U, not K minus 1 is a spin U0 to UK minus 1, and then cycle through it, N times. Likewise, in output data matrix 2, we place a output observation U0, U1, UK minus 1, and then cycle through it. And then we write first subscript shows this, and then final subject this. The dimension of this is actually, so input vector dimension is M, M input, and then P output systems, multi-input, multi-output. So multi-input, you put the K time sequence stuff. So this one M times K, and then you have N column vectors in place. So this one is P times K. Okay. So now here's the trick we use. We consider a particular type of input sequence. Okay, input sequence. So that is actually a very simple case and shown here. We just think about the situations that the output YT is kept to 0, T the negative, and apply an impulse input at the time T equals 3, and then observe the response of a linear time invariant system with the 3 time steps delay. So input is 0, 0, 0, and then actually T equals 3, we just put the one input, boom, the 1, and then after that it's quiet or 0. So if I plot the diagram, so UT is actually blues are basically input in here, okay, and at the T equal 0, it just show 1 and the others are 0, okay. And in response to that, the output to YT is actually we also assume here YT equals 0 in here, and the time T equals 0, it just shows the first input, and then thereafter it shows this kind of impulse response, right? Let's just do some thought experiment, of this input output the sequence. Okay, there's interesting things that happens. So constructing the Henkel matrix for the input U0, U1, and T, you get the basically putting this one into this 0, 0, 0, 1, right? And then cycle through it 0, 0, 1, 0. And then next cycles, 0, 1, 0, 0, right? So this is basically the same sequence as this up to this point, right? And then next column is basically starting here, to here, and I cycle through it, okay? And then the output side is basically here, Y0 is 0, right? Y0 is actually, in here, the 0. This in the time step 3, so Y0 is 0. And then at the time step 3, I said there's something wrong. This is actually step 3. So 0, 1, 2, 3. Okay, so I have to write the 3 here, okay, because that's stated here, 0, 1, 2, 3. Okay, so impulse is given at the time step T equals 3. Okay. So we place these on the output, this sequence into this form. And interestingly, first column is just a G not just shown up here at this step. But this guy is actually Y3, right? Y3, right? So next one, starting with the Y1, 2, 3 shows up, and 4, this guy, right? And then, shows up, all cycle through in this way. Okay. And these actually subscript represent the impulse response index. So it's actually a little different from this time index. Okay. So after that, let's see, continuing this, output side, this guy G1, G2, G3, G4, and the next one G2, blah, blah. And then the input sides are all 0. Input side are all 0. Okay. So if you can actually create this kind of input output data, interestingly, if you see the, lower, right block over here, this guy is basically Henkel Matrix, isn't it? Just push back, Henkel Matrix, boom, boom, boom. Where did I put it in? Yep. Yeah, that, this guy. So, this is actually a the example I talked about is a single input, single output. So I use the lowercase g. So this is multi input, multi output. So I use the capital, G. So G1, G2, G3, right? Press this one, right? Press this one. And we see the same pattern in here. Look at this, G1, G2, G3, G4. Right? So this is a Henkel matrix. So what is good then about the Henkel matrix? Because the Henkel matrix can be represented as the product of observability matrix OK, and then reachability matrix CK. And then by taking the single value decomposition of H, OK and CK can be determined separately. And then from OKCK, we can immediately find the matrix C and then matrix B and then matrix B as well. So once you have this kind of Henkel matrix, boom, you can actually find the ABCD from there. Okay, so that is a technique we like to use. Maybe I should stop my talk at this point and take some questions because it's a little bit actually involved. You hear the many new things, right? Okay, so John Bell, what's the book? I missed the name. It's listed in the course information sheet, reference. Toru Katayama is a textbook, this guy, Toru Katayama, okay? Emily, subspace method for system, yeah, that's right. Why is G not included in the Henkel matrix? Because G naught is kind of obvious, and that's actually determine only D. That's output directly you received. So that can be easily separated out. You can determine D. So focus is ABC. And then ABC are involved, G1, G2, G3, and such. Let me just, quickly, review that where we are. Perhaps. Okay. So just starting with the big picture, we wanted to determine ABCD, and ABCD are linearly involved, so that's good things, right? So we look at the realizations, and first we look at the impulse response and rewriting this. Impulse response can be determined in relation to ABCD matrices. Okay. And interestingly, then we just did a quick, review of observability matrix and controllability or reachability matrix, right? And then here's the things. First introduce the Henkel matrix and then place the impulse response quotient matrix in this way, just to cycle through this guy, right? And interesting, this one can be decomposed to the product factor to a product of the observability matrix and the contributive matrix, right? So once you have a Henkel matrix, we can actually take the next, we introduce the singular value decompositions, and then this sit in the middle diagonal matrix. We can split between this side and then this side, and by taking the square root of it, this is a half sigma matrix, and half of them combined with the U1, and then that's actually observability matrix. The other side is a contributive matrix. Once you get the observability contributive matrix, you can just chop the first block to determine C, and then chop the first block, and here, you can determine B, and then A can be determined the same way, by using this. So, the point is that how you get the, that Henkel matrix, and then take the singular value decomposition. Okay. So, that's actually, starting with the impulse response. So impulse response, given impulse response, ABCD can be obtained. But our goal is to do so starting with the input, the output, the data sequence, right? And then so we introduce yet another, Henkel matrices, for the input, vectors, and the output vectors, big, block Henkel matrices. And, writing this in this way, I put the, up and down over here, U03 and Y03 together in this way. Then look at a very special case. That's actually, we call that the zero input response. All zero except for this part, one impulse. Okay. Then, through this observation, we found that the right bottom block, the 4x4 matrix in this case, is basically Henkel matrix, containing the impulse response vectors, actually, impulse response in, the single input, single output in this case, it's basically, the G1, G2, G3 are actually placed in here. So we have seen that then if we have a Henkel matrix, this can be decomposed to a product of C and then O, observability matrix and the contributivity matrix through singular value decomposition. Okay, that's where we are. Okay, so is that okay up to this point? Is that okay? Yeah.
I have a question.
Sure.
Is it correct that you kind of determine the model order by looking at the number of non-zero singular values in the Henkel matrix? If you have experimental.
That's right. My simple answer is yes, right. If we check the rank condition, that is actually the case. Of course, numerically, quite a few problems, you may face, but I know that's actually the case. But there's nothing wrong to overestimate the dimension of n, and then put the large matrix, and then nothing wrong with it.
Okay, so you wouldn't set like a threshold and truncate.
That's right. But the threshold is very much a subjective thing. So that's causes some problem. There's some more rigorous method than in fact. Okay, with that, let's go back to this story. Okay, so the next, we really want to create that particular type of zero input response. Okay, to isolate the Henkel matrix nicely. Okay, so let's look at the this output equation again, combined with the state the transitions. So y equals cxt plus dut, right? And xt is replaced by axt plus but. Let's do that. And then this xt is to be what I do? I'm sorry, I had to put the I'm sorry. Yeah, yeah. No, yt is given by this. Let's next write the yt plus 1. Yt plus 1 is basically, this one is, yt plus 1, and this becomes xt plus 1. And xt plus 1 can be written axt plus but. So just put in here, we can write in this way. So now we are, moving forward. Yt plus 2, you get the ca square xt, and then ca but, like this. So now collectively, these outputs are now placed in the big vector as shown here. Yt plus 1, Yt plus k minus 1, putting this one this way. Then we like to collect the terms from the right-hand side. First of all, xt is involved in all of these, so we can write, just looking at the first terms together, we can collectively write this one this way, ca minus k minus 1 xt. Sounds familiar? What is this matrix? That's observability extended observability matrix, and okay, right? Right. And then all these terms, it's basically linear basically expressions with respect to ut plus 1, ut plus 2. So let's put the all using here, ut plus 1, ut plus k minus 1. Okay. And we multiply this to these block matrices, right? So it can be collectively written this. Let's check out line by line. Yt equals this guy cxt plus d times ut. Yeah, right here, right? Second line, yt plus 1 ca and xt plus these two terms cb ut and then d ut plus 1. Likewise, you can just get all these terms in this way. So, we just use this kind of representation, collective representation of the output. And sitting here is a observability matrix and a collective input sequence sitting here. And then in between, we have this big matrix. It's a pk times mk matrix. And the structure of this one is interesting. The pattern is a little different from Henkel Matrix, but I'm having some patterns. All diagonal terms actually are the same. Okay, block diagonal terms are the same. And one street away from this main street is sitting here, and they also have the same terms over here. And then two streets from the main street and shown here, basically the same terms. And then the matrix having this structure is called the Toplets matrix. Maybe I scare you with the many different terminologies that you learned today. Henkels, and then actually Toplets, it's a little hard, but let's call this guy Toplets matrix. Okay, so it's a convenient representation. We can clearly separate state from observability matrix, and even sequence from C, B, and A, others. Okay, so collectively, we're using these actually notations. We can write in the YK. This is actually thick YK. Okay, this is still single vector, single dimensional. One line with vector equal OK xt plus this psi k, and the UK is also one vector, big vector. Okay. Now, not only this, we like to write it many of that YK in this way. Maybe I should start with this. So we're getting closer to that the input Henkel block Henkel matrix. Capital Y O K minus 1. First subscript indicate this time, and then the second subscript represent this time index, and we have many of them right in this way, right? So now actually, this is we rewrote this guy, as actually thick big YK. And this guy, the second one, capital, not capital, the thick broad boldface and YK. This index 0 and 1 shows the first index time index here. So this is the YK1, and up to YK n minus 1, Okay. Likewise, input the sequence side, we write this one, in this way, and then write it in many ways in this way. Together with the X naught, and capital X naught is actually concatenations of the state X0 to Xn minus 1. The input and output relationship, this guy, can be expanded to the block Henkel form, because this one is just one of these big column vectors are having this relationship, right? So let's apply this repeatedly for every single column vectors in here. So first one, starting here, OK is the same, but I know on first one, X naught must be placed in here. And then the second one, X1, it must be placed in here, and so forth, right? And this guy too, this is common to all these, stuff. But first one is to pick the capital UK naught, this one. And then second column is, starting here, that's actually, UK2, UK1, excuse me, sitting here, and then going this in this way. So all of this can be written, with all these expanded in the big matrices, input Henkel matrix sitting here, and output Henkel matrix, and observability matrix, and the Topolet matrix. And sitting here is actually even the state is X0, X1, Xn minus 1 is concatenated in this way. Well, there's state X is basically not necessarily a scalar. So this one is actually vector, vector. So this is a matrix, right? Matrix. So all these are matrices. Okay. Maybe you're almost a panic and actually what are actually many things involved. But I know, please bear with me. And this one is a clever things to do. So now we have to assume 3 big assumptions to proceed with the following the things. So first, actually, with this big matrix representation, first assumption is that this X0, X1, Xn minus 1, this collections of state is to be the full rank. X naught matrix is full rank. Each vector is actually n-dimensional. So writing enough, n, capital N vectors, this must be a full rank. So what this means is that the system has to travel, in every axis, in every directions. And then this condition is basically, equivalent to that the system is reachable. And this can be brought to any actually point in the n-dimensional space. That's the first assumption. And assumption 2, A2, is that this input Henkel matrix is actually of rank MK. M is the input vectors dimension, right? And we have so if you look at this, say, if this guy set of input sequence U0, U1, Un minus 1, if this guy is, say, each of them is m-dimensional, if this guy is full rank, rank M, you use the rich variety of input to U and poking all the directions of m-dimensional space. So this one is to be, in the full rank, right? If this one the full rank, one time shift, here, this should be full rank, all full rank, right? So M, K, M full rank matrix is, sitting here, and that is the assumption over here. U not the K1, MK. The third one is that the input Henkel matrix, this guy, and state X naught are basically, not actually, intersecting. So if you take the, concatenated U naught K minus 1 and X naught, you make the big matrix. The rank of this matrix, MK plus N. In other words, even though, we know that X naught is, rank N, and then this one individually, rank MK. But if there's some collinear, row vectors involved in here and here, they are not actually, rank is, is shrinking, right? Shrinking. But if such things do not happen, these two are actually, isolated. Then actually, in the total rank is the rank of this and the rank of this, MK plus N. So, so when this actually assumption is violated, one typical case is you have some feedback control. Input to U is created as a, basically, a linear map of state X, right? So this is the state, just a standard state feedback law. If you do that, U involved here is basically collinear with some components on the X. That actually make this one, not full rank. So don't have the linear state feedback like this form. If that's the case, this assumption is held. So these three assumptions are fundamental in the following the discussion. Now, what we'd like to do is to make the the original this input output sequence, two big Henkel matrices, U naught K minus 1 and Y naught K minus 1. We just put them together. This one is just to make things easier for the notation. This will make things difficult for you. But U and the K and Y are combined to create the so-called data matrix W, data matrix. Okay. Now, interestingly, this data matrix under those three big assumptions, this data matrix can be reduced to this particular form, having a little bit, that the lower triangular matrix form. And if you look at the this particular part, and all the upper part is 0, so basically the 0 input, and then the lower part is basically something, this is equivalent to that Henkel matrix of the impulse response. Okay, so we use this kind of coordinate transformation to reduce this data matrix into this particular form, which includes the 0 input response. So as you have L22, you can apply the singular value decompositions and then create the observability and then controllability matrix separately. Then you can find the ABC matrices. That's it. Okay, so that's what we would like to do. Now, to make this happen, we need to introduce the two lemmas. So these two lemmas are not that complicated, but it's fundamental. So first lemma is that by three assumptions, we also assume that the OK is N. This is actually rank N. Then the following matrix. Now we combine the U and then the Y together. This is basically a data matrix here. This rank 2 Kn plus N. Well, Kn plus N, we assume that's for this matrix, the combining input Henkel matrix and the state X naught Mk plus N. However, under this assumption, rank OK is N, input and output Henkel matrix 2 having the same rank, it's a full rank. And this is actually almost obvious. The proof is something. Y0 K minus 1, this is a big one that we just wrote some time ago. I'm talking about this guy, big representation. So this one, can be written in this way. This is very artificial treatment. U k minus 1, y o k minus 1. Let's write it this way. And then this side, the assumption, made for this matrix, this is full rank, U, O, K, and X, O, right? So, this is, the same. So just pick up the identity matrix. And the second line is important. Y, O, K minus 1 equal phi K, U, and then O, K, X. This is basically exactly the same one as this expression, right? As in this expression. So, this big matrix conversion is actually true. Now that, look at this by assumption number 3, this is full rank Kn plus N, having no state feedback load or something, this one is full rank Kn plus N. And look at this. This is the identity matrix. That's of course full rank. And we assume this observability matrix to be full rank. Then the full rank matrix, this is full rank. This must be full rank Kn plus N. So that's the logic. So this is actually rank Kn plus 1. Yeah, the lemma implies that if we delete the row vectors and in here row vectors, that is actually dependent on the row vectors and U. So U is actually having many of the independent linear independent vectors, right? It may be overlapping with the Y not, but if you eliminate all the overlapping ones here, then how many independent one remains? Still n, state dimension n, independent row vectors remains over here. So this one contains such full rank information. Okay, so here's the key point. Now we think about the any input output pair. Okay, UK and the YK, that's actually input output here. They both are actually extended, time sequence extended one. Okay, but let's make this in a big one vector UK YK, and they must satisfy this relationship, right? UK YK, input output relationship must satisfy this relationship. Okay, now interestingly, under these assumptions, such arbitrary input-output vector can be created by linear combinations of all column vectors involved in your input-output data. So this is actually not involved in the origin of the data, but it can be created by linear combinations of your input-output the data matrix. So if that is the case, maybe in this one we need a little bit, proof for an arbitrary input UK YK that exists in initial state X not that satisfy these conditions, and so you can write this, and therefore this, because this guy is full rank, right? Full rank, this guy should be represented by this. So similar to the previous lemma proof, UKYK present this way, connected to this guy. Here's the input state, but this particular part is basically full rank. So any of them can be represented this way, put in here, combine this, what you have, and here is the input output data matrices. So any input output data pairs can be created by the linear combinations of column vectors involved in your data matrix. So this is actually the mechanisms behind this subspace method. But I know there's actually a very convenient algorithm. It's called the Loq decomposition. So all we need to do is basically, from the previous story, zero input response is very useful, right? As we seen in the previous example. And your original data, input output time sequence put into this big Henkel matrix may not contain that the zero, input response, which is actually conveniently, used for, subsystem method. However, we can actually create such zero input response by taking the linear combinations of your specific data matrix, UK and then YK. And then the previous members showed the existence of LUM, this GZ. So if you just make find many GZs and zetas, zetas like this, and put in this one column wise, you may actually create this form. Remember that this is actually key part because this particular part is zero response part. You may create this kind of form. So from which, by taking the singular value decomposition of this L22 component, this represent the kind of impulse response part, we can actually find the ABCD. So this particular operation can be done very effectively by using the LQ decomposition transforms that are actually applied to the original data matrix. We can actually get this one in just a single shot. So that's actually, LQ decomposition. LQ decomposition is the transpose of so-called QR decomposition. Some of you might have heard of this decomposition, QR decomposition. And actually, LQ decomposition is just, transpose of this version. So any rectangular matrix, real rectangular matrix, that's considered n by n. Such matrix can be decomposed to product of Q and R, and then R is actually having some components here, but all zero left bottom part. So this is actually upper triangular matrix, that's R1, and the Q1, Q2 are basically forming orthogonal matrices and the unit vectors. So this is kind of a coordinate transformation, okay? So every single row column vectors involved here, they have a unit length and they are orthogonal to each other, That is actually, we call that the matrix Q to be orthonormal matrix, okay? So orthonormal matrix, if you just multiply this way and this way, it's just cancel out one or two combinations of zero, and then actually this is having this. So this very convenient decomposition is very much standard, and then it's involved in the MATLAB code QRA. And then what you specify a matrix, a rectangular matrix, and then MATLAB returns Q and R. These two matrices are returned. Okay, and then there's many convenient, good method involved. So we applied this to our problem. So we take the transpose of the QR decomposition. QR decomposition A composed to a Q and R, right? If we take the transpose, A transpose equal, convert the order, R transpose times Q transpose. So this one is exactly our case. Let's actually relate the A transpose to this our data matrix, and then R is basically upper triangular matrix, and turns out to be a lower triangular matrix. So we put in it this way, and the zero sitting here, which is very important, and the Q transpose is sitting here in this way. So with this actually LQ decomposition, we can numerically create the zero input response sitting here, from which we can determine ABCD. And then we continue the next, this on Wednesday. I know two specific well-known methods, MOSEP and Enforcet. These two famous methods can be explained by using this expression. So that's all about it. Sorry, it's just the time is up. Yeah. So I think this one is really, quite intensive materials, and I hope you can go through my slides which are posted, and you need to go through this line by line on your own. Then you can get this method. But this one is, I think it's very useful, very useful. You get some, time sequence, input output data, putting into this method, you get the ABCD matrix. And then not just a random pick of ABCD matrix, but I know it is guaranteed to be minimum. So that's the number of state variables is actually smallest. And I know it is a little bit well-balanced, realizations. Among the many realizations you can get, this is to give you a right one, which is actually, and ready for use, such as the Kalman filtering.